Hi everybody! So in this video we're going to explore different experiments you can do with the Corundum kit from Snellius Minerals. In our previous video we looked at the isotropic versus anisotropic kit, which allows you to understand how to distinguish isotropic and anisotropic materials with a polariscope. So our next step here is actually to further subdivide the anisotropic materials into those which are uniaxial and those which are biaxial. And our corundum is anisotropic and uniaxial. So the corundum kit allows us to better understand the optical properties of uniaxial materials, and we're also going to take a look at the crystallography of corundum and how it relates to the optical properties we end up seeing. So in order to do these experiments yourself, you can pick up a corundum kit at the eBay store Snellius Minerals. The corundum kit has 3 different items in it: a piece of synthetic flame fusion corundum that I've cut in very specific directions and that we will use in order to understand the optical properties of our corundum, a natural corundum sample that will allow us to explore the crystallography of corundum, and a glass marble which, when added to our polariscope as a converging lens, will allow us to generate optic axis interference figures. Unfortunately, the price of natural corundum crystals that would show off the crystallography and be able to show us our optical properties is very high, and so that's why this kit is split into a piece of synthetic corundum for our optical properties and a sample of natural corundum for our crystallography. So the corundum kits are all unique. The synthetic corundum comes in a wide variety of colors, and the natural corundum crystals come in a variety of shapes and colors. However, I've specifically selected these to show off features of the crystallography. So we're going to cover a wide variety of topics in this video, and in order to keep this video short, I'm going to refer you actually to the optical mineralogy playlist. This is a series of videos I've made on optical mineralogy, and in particular the one that's going to be important for our understanding today is optical mineralogy uniaxial materials. And if you want the super deep dive into corundum, you can check out optical mineralogy big picture, or if you're looking for a much shorter video, optical mineralogy big picture summary. So the goal of the optical mineralogy videos is to help folks understand how a variety of complicated concepts are actually all interrelated. And so in the case of our minerals, a mineral is defined by its chemistry and structure. And the chemistry and structure of our mineral ultimately result in the crystallography that we see, as well as the optical properties that we see. And so all of these concepts are actually interrelated with one another. And so by knowing any 2 of the pieces of our triangle of concepts here, we can usually figure out the 3rd missing piece. So if I know the crystallography and optical properties of a material, I can often identify it. Or if I know the identity of material, I can combine that with the optical properties that we see in order to tell you the crystallographic direction you're looking along that material. So let's begin with some background information on corundum, and then take a look at our natural corundum sample in order to understand the crystallography of corundum. So our corundum is composed of aluminum oxide, Al2O3. The structure of corundum can be thought of as having oxygen in a hexagonally closest packed arrangement, with aluminum occupying 2/3 of the octahedral interstices between our oxygen atoms. This places the aluminum in an octahedral coordination. The structure and chemistry of corundum yields a material with a high hardness. Corundum has a hardness of 9 on the Mohs scale. The structure and chemistry further result in a material that has no cleavage planes, so no preferential directions of weakness in this structure, and corundum is also respectively dense at around 4 grams per cubic centimeter. These factors often lead to corundum forming placer deposits, as corundum is hard, chemically inert, and respectively dense, and this allows it to be separated from other sediments using that difference in density. The structure of corundum leads to our symmetry point group of 3 bar 2/m. This point group symbol means that we'll have one threefold rotoinversion axis as our c-crystallographic axis of our corundum, and there will also be three twofold axes with perpendicular mirror planes. The twofold axes will be our a-crystallographic axes. Don't worry, we'll go through this in more detail in a bit. Since our corundum is in the trigonal crystal system, that means it will have to be uniaxial with respect to its optical properties, and so our corundum will be defined by two refractive indices, epsilon and omega. In particular for corundum, because epsilon is less than omega, corundum is uniaxial negative. So now that we have some background information on corundum, let's take a look at the crystallography of our natural corundum sample, remembering at the same time that this crystallography is actually being determined by the chemistry and structure of our corundum. So here we have a natural crystal of corundum. You can tell that this was probably associated with a placer deposit. You can see it's worn around the edges. Right now we're viewing this sample in normal light, and the shape we're seeing with our sample is predominantly a hexagonal prism. Corundum is a member of the point group 3 bar 2 over m. And this point group symbol is actually telling us the symmetry operations we want to look for. So as a member of the crystal class 3 bar 2 over m, corundum will have a threefold rotoinversion axis as its c-crystallographic axis, and in a plane perpendicular to that c-crystallographic axis, there will be three twofold rotational axes perpendicular to mirror planes. The twofold rotational axes will be our a-crystallographic axes. So the hexagonal shape we're seeing here may suggest that there is a sixfold rotation axis going on, but in reality what we're seeing is a threefold rotoinversion axis, and this crystal also has a couple other features modifying it, letting you know that the symmetry element that we're seeing here isn't as simple as a sixfold rotation axis. A problem with using visible symmetry elements to determine our point group is that crystals of a lower crystal class or a less symmetric point group can sometimes masquerade as crystals of a more symmetrical class, depending on the particular crystal forms present. Basically, what I really need is a crystal form to cut both the A and C axes simultaneously for our corundum crystal, so that threefold rotoinversion axis can put in some work and show us an awesome rhombohedron. So given all that, in this direction, what we're actually seeing is the threefold rotoinversion axis of our corundum, and this is our c-crystallographic axis. So we are looking down the c-axis in this view. Our a-axes will then lie in a perpendicular plane, and these will be twofold rotational axes, and then perpendicular to our a-axes will be mirror planes. So let's rotate the crystal 90 degrees now, and we can take a look at the crystal viewing along one of our a-crystallographic axes. So once again, what we're predominantly seeing here is a tapered hexagonal prism, but after I improve the focus, what you'll be able to see is, in addition to our hexagonal prism, it's also being modified by two very distinct planes cutting off the upper right and lower left corner of our crystal. So overall, our crystal looks pretty weathered, but these two planes, if we were to look at the faces here, are actually much fresher and much better looking than the rest of the crystal overall. These two planes are actually caused by parting in the corundum crystal. Whereas cleavage is a pattern of breakage caused by structural weakness in particular directions through a crystal, and is present in all examples of a mineral, parting is usually caused by other factors that don't necessarily need to be present in every example of a mineral. In the case of corundum, this is caused by either the exsolution or alteration of boehmite into very distinct planes in the corundum crystal structure. These boehmite to corundum contacts are then weaker than the structure overall, and so when these crystals break, they tend to break along these very nice, well-defined planes. If you want a deeper dive into what's going on here, I suggest you check out the paper Boehmite Exsolution in Corundum. Because the directions of these partings are actually crystallographically controlled, they're also telling us something important about the symmetry of our corundum crystal. And in the case of these partings, they're actually going to help us out a lot. because the partings will actually break into a rhombohedral pattern, allowing us to see the true 3-bar 2/m symmetry of our corundum. Here you can see an image of a different corundum crystal where these planes of boehmite are very distinct. Taken together as partings, these 3 planes would generate a rhombohedron. Back to our original crystal, however, we only really have 2 of the total 6 different fractures we'd need in order to see a rhombohedron. But knowing that those 2 planes are actually part of a rhombohedron helps us to set where exactly our a-axes are for this crystal. Our a-axes will be 2 folds perpendicular to mirror planes, and in order to have that line up with our rhombohedron, they have to be located here. So we've tied down our crystallographic axes for 2 different views through our crystal. Let's also take a look at the mirror plane that we were talking about earlier, perpendicular to our a-axes, which will be located here in the corundum crystal. You can also see from this view how that rhombohedral parting is a bit fresher than the rest of our crystal. So the natural corundum samples in our corundum kit are going to consist of a wide variety of shapes, because you have both the growth form, which usually is something like a hexagonal prism terminated by a pinacoid, but then you have that form being modified by these rhombohedral partings as well. So just a couple more examples of what you might get as your natural corundum sample in the corundum kit. These are all, of course, unique, but I do try and select things that are fairly straightforward as to what's going on with a combination of growth form and parting. In this crystal, it would be a little bit harder for you to mistake the C-axis as a 6-fold, given all the triangles we see here going on, which I think are some combination of both growth forms and then also the parting directions that we were talking about earlier. Here's a view down one of the A-axes for this crystal. Next up, we have a corundum crystal that displays parting rather well. It's had one very distinct break. And so what effectively we're seeing here is a hexagonal prism that has had one very nice rhombohedral slice chopped off it. This view down the A-axis really shows this off. So hopefully you feel comfortable using symmetry, forms, and parting directions in order to orient your corundum sample crystallographically. So going back out to the big picture, I mentioned before that our corundum is defined by its chemistry and structure, and that these ultimately determine our crystallography as well as optical properties. And so what I actually want to do is bring in a structure model of our corundum at this point without getting into too many details about where it came from, which I'll leave for the optical mineralogy big picture video. So here we have a corundum structure model with aluminum being represented as small metallic ball bearings and oxygen being represented as glass spheres. And just a note, at this scale, what we're looking at is space group symmetry with these symmetry elements shown. We've got our macro scale corundum crystallography and point group symmetry. And looking at these side by side, you can see how the macro scale crystallography that we see is actually a product of what's going on at the micro scale with our crystal. So let's do the same exercise, taking a look down one of the A-axes of our crystal. So we're looking at the micro scale. Here's the same view at the macro scale with our crystal. And then here's those 2 views side by side. So while it's delightfully nerdy to look at how the microscopic structure of corundum influences the morphology of macroscopic crystals of corundum, it's a bit more important than just that. We can actually use this to our advantage, because the microscopic structure of corundum is going to control a whole bunch of different physical properties that vary with direction in the mineral. And not only physical properties, but chemical properties too. So properties that vary with direction in our crystal can include things like hardness, thermal conductivity, electrical conductivity, our optical properties, which is what we're going to focus on here, rates of various chemical reactions, and cleavage in addition to others. So going back to our triangle of big picture concepts, if we know that we have the mineral corundum, and we have a nice macroscopic crystal where we can identify the crystallography, I can tell you the optical properties that we'll see based on that knowledge. Alright, so now that we've oriented our natural corundum samples crystallographically, let's talk about the optical properties we would be able to see if we could get light through them. So in order to do that, we're going to take a look at the optical indicatrix for corundum. The optical indicatrix is a three-dimensional representation of the refractive indices in our corundum. And note that the shape of our optical indicatrix is highly exaggerated for demonstration purposes. And so the first thing I want you to note here is that our refractive indices align nicely with our crystallographic axes for corundum. And this alignment between our crystallographic axes and our refractive indices is the same for all of our uniaxial materials. Refractive index epsilon aligns with our c-crystallographic axis, and refractive index omega aligns with the plane of our a-axes. So it then becomes rather trivial to predict our optical properties based on crystallographic direction. Our views along the plane of the a-axes will exhibit the maximum birefringence, or difference between refractive indices for our corundum. If we are viewing our corundum sample in plane polarized light, these views along the plane of the a-axes can exhibit pleochroism. We will be able to see one pleochroic end-member color associated with epsilon, and another associated with omega, along with intermediary colors that are fractions of epsilon and omega as we rotate our sample. With crossed polarizers, this view will exhibit the extinction and transmission of light as we rotate our sample. When our plane polarized light source is aligned with either epsilon or omega, no light will be transmitted through crossed polarizers. But light will be transmitted with crossed polarizers when our plane polarized light is aligned with neither epsilon nor omega. The brightness of this transmitted light will be greatest when we are 45 degrees from aligning our plane polarized light with either epsilon or omega. This light that we are seeing with crossed polarizers is an interference color, and if we knew the thickness of our sample, we could use that color to determine the birefringence, the difference between epsilon and omega. However, this would be most useful in thin section. With a thicker sample, the interference color just appears as white light, and so it really isn't that helpful to us here. This view down the plane of the a-axis will also generate a flash interference figure. So let's move on to our view through the crystal looking along the c-axis. This view is looking along the optic axis, and so we will only see light associated with refractive index omega. And so this is the one view through our corundum where it behaves very similarly to an isotropic substance. As such, this view does not exhibit pleochroism in plane polarized light, but makes this view useful to us because we can figure out which pleochroic end-member color is actually associated with omega. With crossed polarizers, this view remains at extinction, as light is only interacting with refractive index omega. This view will generate a uniaxial optic axis interference figure. So as I said before, our natural corundum sample really isn't up to the task of transmitting light, and if it were, it would be very, very expensive. So I can't really show you the optical properties in our natural sample of corundum, but let's go about this a different way. Let's take a look at our synthetic corundum sample in order to investigate the optical properties of corundum. And with this, we'll actually be able to determine the crystallographic direction we're viewing through our sample based on those optical properties. So here's one of the synthetic corundum flame fusion samples from our corundum kit. And these come in a wide variety of colors, but they are all cut so that the windows into the corundum are looking either down the plane of the a-axis or along the c-crystallographic axis. So if you watch the optical mineralogy uniaxial materials video, you'll notice that a bunch of this is repetition, but that's because with your synthetic corundum from the corundum kit, we can essentially do the same experiments that we did at the end of the optical mineralogy uniaxial materials video. So your synthetic corundum sample was cut from a larger boule of synthetic corundum. The way these were cut results in 2 faces left over from our original bowl, and then 4 faces that I've cut and polished. It's also important to note that with our synthetic corundum samples, some colors have the colorant actually concentrated at the outer edge of the boule, and so we have to be aware of this when we're looking at pleochroism. So we're currently viewing our synthetic corundum sample in our polariscope, and right now we're viewing it with transmitted plane polarized light that is vibrating in a north-south direction. So let's rotate our sample and see if we can notice any pleochroism in plane polarized light. So as we spin the sample, you can notice the color become darker and more purple. Since we see pleochroism, we know that this direction through the corundum crystal is not the optic axis. And if I did a good job cutting the corundum, that means we're looking down the plane of the A-axes. This plane will have the maximum difference between refractive indices, and also the maximum difference between pleochroic colors. Many views through our corundum crystal will exhibit pleochroism, but only views down the plane of the A-axes, also known as the circular section, will exhibit the maximum amount of pleochroism. Let's reset our sample to its original position, and now let's view our sample with crossed polarizers and see what happens. As the upper polarizer comes in, we see that the sample is at extinction. This means that our plane polarized light is aligned with either epsilon or omega. As we rotate the corundum, light starts to transmit through our upper polarizer. We reach a maximum brightness, and then we continue back to extinction with further rotation. Once again, we must now be aligned with either epsilon or omega. So let's now flip our synthetic corundum sample onto a different viewing face and observe how it behaves in plane polarized light. So as we begin to rotate our corundum sample with this viewing direction, you'll notice that not really much of anything is happening. So we're not seeing any pleochroism in this direction. And what this means is that we're viewing our corundum along the optic axis and along the c-crystallographic axis. This also means that the pleochroic end member color that we're seeing here is associated with refractive index omega. So this viewing direction through our crystal has shown us that omega is associated with the darker purple pleochroism end member color. This means that epsilon is associated with the lighter pink color that we saw earlier. This is one of the reasons why the view down the optic axis of our crystal is important, because we know in this view that we are only seeing omega. So let's summarize our results of looking at our corundum sample in plane polarized light. So far with our corundum sample, we have one view where we can observe pleochroism, and another view where we don't observe any pleochroism. Let's continue looking down the optic axis of our sample, but now let's look with crossed polarizers. We should expect to see the sample at extinction when viewing along the optic axis with crossed polarizers, because this is the direction through our uniaxial material that should behave like an isotropic substance does. However, that's not quite what we see. We'll rotate the sample a bit now to see if anything changes. So something strange is going on here, and in part what we're seeing is a result of this being a flame fusion synthetic material. The flame fusion or Verneuil process results in a whole bunch of stress remaining in the corundum produced. Mechanical stress is one of the things that can make isotropic materials behave anisotropically. This is part of the reason why we're seeing waves of extinction occur as we rotate our sample. You'll also notice some fun red and blue colors show up as we rotate the sample. And we can use these first order red and second order blue interference colors to get an idea of how far off of the optic axis I've cut this, along with how much the stress is messing with our refractive indices. For our view of our corundum sample looking down the plane of the A-axes, the crystal is quite thick and the difference in our refractive indices is large enough that our interference color just ends up looking like white light. If we had a very thin slice of a crystal that we actually knew the thickness of, we could use the interference color to actually determine the birefringence of our crystal in that view. Let's actually try this math out now for our current view through our corundum crystal. Note that your interference colors might be slightly different, based on how accurate I was in cutting the corundum and also the stress remaining in the structure. So, the following equation is going to be useful to us. delta equals d times n2 minus n1. Delta is the retardation that we've observed in the form of an interference color, d is the thickness of our sample, and n2 minus n1 is the birefringence of our sample. So the first order red interference color that we've observed corresponds to a retardation of around 400 nanometers. The thickness of this particular sample is around 7 millimeters, which corresponds to 7 million nanometers. Usually when you're using this equation, you're looking at a thin section, which is 30 microns or 30,000 nanometers. So this is a bit unusual to be doing this with a sample so thick. With our numbers, we can come up with an estimate of our birefringence, n2 minus n1. And we get a value of 0.00006, which is really tiny, which is also the only way we'd ever see a first or second order interference color in a sample this thick. So with a birefringence value that small, I also feel pretty good about having cut my corundum crystal very close to the optic axis, which is what I intended to do. So that bit of math there took us a little bit on a tangent, but now let's get back to the bigger picture view of what's going on here. So we've identified views looking down the optic axis and the circular section of our corundum. By using our optical properties, we know where our A-axes are and our C-axis is of our corundum crystal. So we have one more view to look through our synthetic corundum, given how I cut the sample. This view should also be looking along the circular section and A-axes of our corundum, but let's take a look just to make sure. We're doing this view through our corundum last, because the view through the non-polished faces of our corundum actually has the most complications. So for this particular corundum sample, this view is actually going to be looking through the band of colorant concentrated at the outside of our sample, and so you'll notice the colors here are a bit different than our earlier pleochroic scheme, and it's just because we're actually looking through that band of colorant. Also, with this view, you want to be careful not to accidentally scratch your polariscope because these faces are not polished, as we're looking through a fracture face and the outer edge of our boule. So let's rotate our sample with this view and see if it exhibits pleochroism. And as before, we start out with a lighter color, and as we rotate the sample, this gradually darkens. Now we'll reset and look at our sample with crossed polarizers. So we learned with our other view that epsilon is associated with the lighter pleochroism end member color, and so as no light is being transmitted right now, we must actually be aligned with refractive index epsilon. And we begin to spin and the sample starts to transmit light, and eventually we align our plane polarized light with omega, and the sample is once again at extinction. So now that we've looked through all the directions of the corundum sample that we can, let's summarize our findings. We essentially have two views through our corundum sample that are looking along the circular section and the plane of our a-crystallographic axes. These views exhibit pleochroism in plane polarized light, and the extinction and transmission of light with crossed polarizers. There is one view through our corundum sample that is looking along the optic axis and C-axis of our crystal. This view does not exhibit pleochroism in plane polarized light, and exhibits mostly extinction with crossed polarizers. It doesn't quite live up to the ideal with crossed polarizers because of residual stress in the corundum crystal structure, as well as less than perfect lapidary skills on my part. So let's use our corundum sample to generate some interference figures now. And for this, we need to add an additional part onto our polariscope. We need to also have a converging lens. So that's why there is a marble included in the corundum kit. We can use this as our converging lens in order to generate an interference figure. So let's go back to our schematic diagram for a polariscope. And so in order to generate an interference figure, what we're going to do is start out with our polariscope set up for viewing a sample with crossed polarizers. And what we're going to do is add our converging lens above the upper polarizer in order to generate an interference figure. But also, we could add our converging lens below the upper polarizer to generate an interference figure. I've had success here with either of these setups and think it's probably down to the geometry of your polariscope which one of these will end up working better for you. And speaking of polariscope geometry, it's going to take a bit of finagling to get these distances just right between our different components. And so play around with these distances and see what works for your polariscope. So let's get back to our corundum sample now and try and generate interference figures for our different views through our corundum. Corundum is a uniaxial material, and so we should be able to generate a uniaxial optic axis interference figure when looking down the optic axis of our corundum. So let's try this out and see what happens. Right now we're looking at our corundum with crossed polarizers. And as you can see here, the crystal appears further away because I had to actually change my focal distance in order to generate this interference figure appropriately. So we need to bring one more additional piece into our view in order to generate our interference figure, and that's a converging lens. In this case, I actually used a hand lens instead of a marble because it provides a bit wider field of view, but they're functionally equivalent as converging lenses. So it takes a bit of finagling to get to the appropriate focal distance, but when we do, you can see a uniaxial optic axis interference figure. And so what we see here is a uniaxial cross with colored isochromes radiating out from the center of that cross. Here's a quick diagram of some of the important parts of our uniaxial optic axis interference figure. So you should check out the educational video Improved Uniaxial Optic Axis Interference Figures if you want a deeper dive onto what this figure represents. But for our purposes, the ability to generate this interference figure is telling us that this material is uniaxial. However, there are some caveats with our synthetic corundum samples. You may notice that the isogyres, the dark bands that make up our uniaxial cross, actually appear to split apart from one another as we move our view around our crystal. And this segment of video shows this well. Once again, our corundum sample is deviating from the ideal due to the stress within the sample. So when generating an interference figure, we also want to rotate the mineral sample itself in order to observe how the interference figure behaves. So in order to do that, I reset our view here and set up a little stand for my upper polarizer. And now you get to watch me attempt to coordinate holding a hand lens while rotating a mineral at the same time. So if our mineral is indeed uniaxial, our interference figure shouldn't change from the uniaxial cross even as we rotate it. And for the most part, as our sample rotates, it does maintain that uniaxial cross. Of course, once again, there's some stress going on in our corundum, and that's messing with things a little bit as we rotate the sample. Also, as we rotate the sample, the center of our uniaxial cross should stay in the center of our field of view. If it starts to wander from the center of the field of view, that means we're a bit off axis with our cut. And as you can see here, the center of that cross stays pretty much in place, which means we did a pretty good job of cutting our corundum so that we're actually looking down the optic axis. Let's now flip our corundum sample onto a different face so that we're looking down the plane of the a-axis. And with this view, we should be able to generate a flash interference figure. We'll start off with rotating our sample 45 degrees from having our plane polarized light align with either epsilon or omega. And then we'll bring in our hand lens for a converging lens in order to view our flash figure. So with the flash interference figure, we rotate our crystal, and what happens is the crystal rapidly transitions from the transmission of light to extinction as diffuse isogyres take over our field of view. So here's how the flash interference figure looks for our corundum sample. Now the flash interference figure doesn't look as awesome as the optic axis interference figure looks. But the flash interference figure does tell us something important. If we can correctly identify a flash interference figure, that means that we're looking down the plane of the a-axis of our sample. So let's get back out to the bigger picture of what's going on here. When we were looking at our natural corundum samples, we could use our crystallographic forms to determine our crystallographic axes, and then make predictions about the optical properties that we could see in particular directions through our crystal. Unfortunately, we couldn't observe these optical properties firsthand due to the quality of these crystals. With our synthetic corundum sample, however, we could use our crystal's optical properties in order to determine the crystallographic direction in which we were looking through our sample. Here's how our optical properties stack up with different directions through our corundum sample. And after identifying directions through our corundum associated with these optical properties, we can now add on crystallographic axes to our synthetic corundum. Hooray! We've oriented our synthetic corundum in space! Also, an important caveat here, I don't know the location of each individual A-axis in our synthetic corundum crystal. What I've learned using the optical properties is the location of the plane of the A-axes. After all this, you may be wondering, well, why should I care? And one of the reasons why this is important from my perspective is that you can combine your crystallography and optical properties in order to identify unknown minerals. So this would be an important use for mineralogists and geologists, but this information is also important to many other fields, including things like material science. For example, corundum is used in some high-tech materials applications, including scratch-resistant and chemical-resistant windows for scientific instrumentation. Given the anisotropy of our corundum, if you're going to make a window out of it, you probably want to make a window looking down the c-crystallographic axis. And we can figure out the location of the c-crystallographic axis by either using our crystallography or our optical properties. Corundum is also anisotropic with respect to physical properties other than just our optical properties. Another application for corundum is in precision bearings and other mechanical parts. Orienting corundum appropriately for these parts may help increase the longevity of the part and also manage the wear on the part over time. As corundum is often used in jewelry, understanding the optical properties of corundum can also be important to lapidaries. Lapidaries can use what we talked about today in order to orient a piece so as to maximize a particular color. And how corundum takes a polish actually varies with crystallographic direction as well. These properties are also important to gemologists who are trying to sort real from fake. And chemists can also make use of this information, as chemical reaction rates will vary with crystallographic direction. Also, on a very non-pragmatic level, I think that understanding these properties is key to understanding a deeper beauty about the world around us. So let's review some of the big picture concepts that the corundum kit can help us explore. First off, the corundum kit consists of a natural sample of corundum that we can use to determine the crystallography of natural crystals, a synthetic sample of flame fusion corundum cut in very specific directions so that we can determine the optical properties of our corundum, and a marble which we can add to our polariscope setup as a converging lens in order to generate interference figures. With our natural corundum crystal sample, we were able to identify our crystallographic axes based upon growth forms and partings. And we then used the optical indicatrix for corundum to determine the different optical properties we'd see in different directions through our crystal. However, our natural sample is unable to transmit light, and so we transitioned to looking at the synthetic corundum sample in order to understand the optical properties of corundum. This synthetic corundum sample is cut so that we're forced to look down either the optic axis of our corundum or the circular section of our corundum. So in viewing our synthetic corundum sample with plane polarized light, we end up with two viewing directions that exhibit pleochroism and one that does not. The two viewing directions that exhibit pleochroism in plane polarized light exhibit the extinction and transmission of light with crossed polarizers. So for these directions through our synthetic corundum, we're looking along the circular section of our optical indicatrix and the plane of the A-axes of our crystal. Back to the direction through our crystal that did not exhibit pleochroism, with crossed polarizers we see mostly extinction. However, this direction through our crystal deviates a bit from the ideal due to stress remaining in the corundum crystal structure and being slightly off-axis with the lapidary cut made here. This view through our corundum has us looking along the optic axis of our corundum and along the c-crystallographic axis. This direction through our sample allows us to generate a uniaxial optic axis interference figure. But once again, the behavior is a bit less than ideal because of the stress remaining in our corundum structure. Our other two viewing directions through our corundum crystal, looking down the circular section and the plane of the A-axes, allow us to generate flash interference figures. We then gathered together our optical observations for our synthetic corundum and used our optical properties to orient our synthetic samples crystallographically. So hopefully these experiments with the corundum kit have helped you understand the interrelationship between our big picture concepts in greater depth. And here's one last shot at bringing all the important stuff together. Our mineral corundum is defined by its chemistry and structure. In turn, the chemistry and structure of our corundum determine the crystallography that we see macroscopically, as well as the optical properties we end up seeing. So thanks again for watching this video. You can pick up the corundum kit from the eBay store Snellius Minerals at the following web address. If you have any questions, comments, or concerns, feel free to email me at snelliusminerals@gmail.com. Here are the references used in the creation of this video. And our next video is going to investigate the optical properties of quartz. And in order to do that, we're going to look at a slice of natural quartz crystal. So thanks again for watching, and have a great day.